optimal, well, we're looking if dogs can come up with the optimal calculus so that it can retain its energy when it comes to, or just reach the target faster. If there was a drowning person in the ocean and the dog in A is reaching B, which is the drowning person. And we're seeing if dogs have the innate ability to reach that point with the perfect calculus. So I will first introduce the different values we have in this graph. So z minus y z as in A to C, z minus y and y here. Z minus y would be how much he is running, because we want him to run to a certain point, in this case D, before he swims to the target. And the distance from him swimming to the point B would be x squared plus y squared to the square root. And we know in this case that x is constant because the person is not drifting farther away. And to come up with this idea, we need to know the rates that the dog can run and the dog can swim. So essentially, if the dog can run faster, then he'll want to run more before he swims. If the dog can swim faster, then he'll want to run less and swim more. So in this case, we used R and S to differentiate between the rates of it running and it swimming. So R is how fast it can run, and S is how fast it can swim. And in this case, if the ability is, if it can run faster than it can swim, then we assume that it's going to run more. And in this case, because the y here is between is the distance between D and C, we can assume that the y would be less than x, which is the constant, because it wants to swim less. And if it swims faster, then we'd assume that the x would be smaller than y. So then its y would be greater, so then it will have to swim more, which it likes because it swims faster. And in the case that the rate of running and swimming is the same, then we assume that the x and y would be the same. So x will equal to y, because this makes a perfect equilateral triangle, and the hypotenuse would be minimized due to that. And it will run to a certain distance before it swims. It will always have to swim. And so by coming up with the distance that it is running and the distance that it is swimming, we come up with the equation where t of y is the time, and z minus y is my distance running, and r is the rate that I run plus how much I'm swimming divided by my rate of swimming.
Okay, so in part 2, some guy with his dog did the actual experiment where he calculated the time it took for the dog to either run 20 meters or swim 10 meters. And these are the times here that they gave us. So from those times, because they gave us the distance and the time, you can calculate rate, which is what we did here for both of them. And then after that, we calculated the average rate of the entire data plot. And from that, we saw that his running time,
Speed.
or running rate, speed, whatever,
Yeah.
is greater than his swimming speed, which was expected because dogs can run faster than they can swim. So from that, we can conclude that this is the scenario that we need to use for this experiment where rate is greater than time, therefore the distance here, x, is greater than the distance y here. Therefore means the dog is going to run more, and so it has to swim less in terms of here.
Go.
All right, as Albert said, this is our function that we created. So then we, on part 3, we use the actual z value that was given to us in the problem, which is 15 meters. And the 6.354 was our average value that Mitchell mentioned earlier that we found. And then 0.874 was the average swimming speed. And then that was equal to the total time, which is what we're trying to find. And then we plugged in the average x values. Well, the average x value is 11.75. Using the 35 points that were also given to us in the problem. And this y is the average y values that were given to us, and it's supposed to be 1.38 1.983. But our optimal value that we found is y equals 1.6317, and how we found that is from plugging in all the values that we found. So x is 11.75, and we plugged in x because it's our constant value, and from there we found figured out that it works for the point that Mitchell mentioned earlier, that x is greater than y, because the dog can run faster than it can swim. And so going back to the function, we plugged in all the values and then took the derivative to find our critical point, which I mentioned earlier was 1.6317 meters per second.
Just meters.
Just meters. And then, so, yeah.
Compare the values.
Our average value that we found was 1.983, and the one that we figured out was y equals 1.6317, and it's about like a 0.3 difference.
Okay, so just some general conclusions about what we solved in this problem. So, in the context of this scenario, y is the optimal distance that the dog should travel, as calculated via our critical points. And the first thing to note here is that these values, the optimal one that we calculated versus the experimental one that we derived from the data, are relatively similar. So we can infer by this that dogs do have some innate ability to have calculus in their brains and know what the fastest route to a given target is. So that's very interesting, and obviously we can see that from these numbers we can derive what the optimal distance is on land, or that a dog should swim versus what the experimental distance is he should swim, and what the optimal distance he should run is versus what the optimal distance he should run is. And the important thing to note is that these values are all pretty similar, which is consistent, and it agrees somewhat with the logic that dogs have some innate sense of calculus. But there are some assumptions and limitations to this experiment which are noted. One is that x is constant. When there is an object in the water that is out there, we cannot assume that everything is ceteris paribus, all things equal, and that the object is remaining still. There is every reason to believe that the object could be moving farther away, being pushed out by the wind or by the waves, and therefore derivating, which means it is not constant. Secondarily, during the experiment, there were data points that were thrown away when the dog immediately jumped in the water and refused to travel on land before jumping in the water. These would skew these data points and make these slightly different figures, which would somewhat repudiate the argument that there is an innate sense of calculus within dogs. Building upon that, there was only one dog used. We don't know if different breeds of dogs, if a different dog had different training, if that would have impacted the way that this dog would have behaved when chasing the target. And for dogs, like any animal which engages in respiration, will get tired over time. And as the waves grew taller over time, he could become more tired, which would impact the time and the decision making of the dog. But in conclusion, these are our values. They're relatively consistent, so there is some validity to the argument that dogs have the ability to compute calculus. Thank you.